Hi everyone. In the second lecture of investigation of molecular structure, we have discussed the difference between the non-polar and the polar molecule and the molar polarization for the non-polar molecule. So friends, all of you know that. So here in case of the non-polar molecule, the center of positive charge, that is the nuclei, and the center of negative charge, that is the electrons, these two centers, they are coincide with each other. They are at the same position, they are not away from each other. So such molecules are called as the non-polar molecule. So here the non-polar molecule, they does not have the dipole moment. Their dipole moment mu, it is equal to 0. In case of the polar molecule, the center of positive charge, that is the nuclei, and the center of negative charge, that is the electrons, they are not coincide with each other, they are away from each other. So here such molecules, they are called as the polar molecules. So here the polar and the non-polar molecule. In case of the polar molecule, so polar molecule have the permanent dipole moment, that is the mu, it is not equal to 0. And here all of you know that dipole moment, it has the unit dBi, 1 dBi, or 1 dBi is equal to 10 raised to minus 18 centimeter or ESU centimeter. So here the unit for the dipole moment, it is the dBi. That means here dipole moment is expressed in terms of the dBi or in terms of ESU centimeter. Then here the molar polarization in case of the non-polar molecule. So here when the in case of the non-polar molecule, the center of positive charge and the center of negative charges, they are coincide with each other when the electric field is applied. So here the usual distortion of the positive and negative charges would occur, giving rise to the induced polarization. And in case of the non-polar molecule, the induced polarization, it is denoted by symbol Pi or Pm. So it is equal to capital D minus 1 divided by capital D plus 2 into m by d. So by substituting the value of the dielectric constant d, molecular weight of the substance m, and here the d is the density, we can determine the induced polarization. If we know the polarizability of the molecule, that is alpha, then induced polarization Pi is equal to 4 by 3 pi n alpha, where alpha is the polarizability. So in this way, we can determine the molar polarization in case of the non-polar molecule. In this lecture, we are going to discuss the molar polarization in case of the polar molecule. So here again, in case of the polar molecule, the center of positive charge and the center of negative charge, they does not coincide. So here all of you know that the dipole moment mu, it is given by the equation mu is equal to Z into L. Z is the this is the electric charge, while L is the distance between the positive and negative center. So here in case of non-polar molecule, this L is equal to 0, but here in case of the polar molecule, L is not equal to 0. So here mu is equal to Z into L. And here in case of the non-polar molecule, when the in case of non-polar molecule, when the electric field is applied, there is only induced polarization. But here in case of the polar molecule, when the polar molecule, when it is placed in the electric field, two types of effects are observed. So here the first effect is our regular induced polarization. The field will tend to polarize the molecule, that is the induced polarization. This is the first effect. Then here the second effect, the electric field will tend to rotate and orient the permanent dipoles in the direction of the field. So this effect, it is called as the orientation polarization. So in case of the polar molecule, there are two types of the polarization. So induced polarization as well as the orientation polarization in case of polar molecule. So let us consider this diagram. So what is this? Molecular dipoles in the presence of electric field and orientation polarization. So this is the positive plate, this is the negative plate, this is the polar molecule. Here in case of the polar molecule, the center of positive charge and the center of negative charge, they are not coincide with each other, they are away from each other. So here all of you know that when the electric field is applied, the center of positive charge, it is attracted toward the negative plate, and the center of negative charge, it is attracted toward the positive plate. So here in the absence of the electric field, what happened? So here in the absence of the electric field, so a polar molecule has the positive and negative end. So here in the absence of an electric field, the molecules and hence the molecular dipoles, they are randomly distributed in all direction due to the thermal effect. In case of in case of the absence of the electric field. So, here the molecules and molecular dipoles, they are randomly distributed. So, positive end is close to positive end or negative end is close to negative end. So, here in the absence of electric field, molecules and molecular dipoles, they are randomly distributed. But here what happen, when electric field is applied, there will arises two disturbing effect. So, here the first effect is, that is a usual distortion of the positive and negative charges would occur, giving rise to the induced polarization. That means, here this positive end, it is attracted toward the negative plate, while the negative end, it is attracted toward the positive plate. So, here this is the induced polarization, this is the first effect. Then here the second effect is very important. So, in the second effect, the field would tend to orient all the molecule in the direction of the field, the positive end pointing toward the negative plate. So, positive end pointing toward the negative plate, and but the thermal agitation would oppose such a orientation, and the molecules would take up some intermediate mean position between the direction of the field and their original position. So, here this is the intermediate position between the direction of the field and the original position. This effect of the field on the dipole, it is called as the orientation polarization. So, here this is the orientation polarization. So, in case of the polar molecule, there are two types of the polarization, induced polarization as well as the orientation polarization. So, here the usual distortion of the positive and negative charges would occur, giving rise to the induced polarization. This is the first polarization, and the second one is the orientation polarization. So, there are two types of the polarization. So, in case of polar molecule, Pm is equal to Pi plus PO. So, Pi is the induced polarization and PO is the orientation polarization. That is, the Pm or Pt is equal to, again it is given by the same equation, capital D minus 1 divided by D plus 2 into m by D. Again here capital D is the dielectric constant, m is the molecular weight, D is the density. By substituting the values of dielectric constant, molecular weight and the density, here we can find out the Pt or the total polarization of the given substance. Then Pt is equal to Pi plus PO. Pi is the induced polarization and PO is the orientation polarization. So, friends, here in case of the polar molecule, there are two types of the polarization, induced polarization as well as the orientation polarization. Then here but we know that the induced polarization is given by the Clausius and Mausserti equation. So, all of you know that the equation Pi is equal to 4 by 3 pi n alpha, where alpha is the polarizability of the molecule. Further, here Debye showed orientation polarization, it is given by the equation, that is the PO is equal to 4 by 3 pi n mu square divided by thrice kT. So, here in this equation mu is the permanent dipole moment, mu is the dipole moment, K is the Boltzmann constant and its value is 1.38 into 10 raised to minus 16 ergs per degree per molecule. Then here n is the Avogadro number, pi is constant, it is 3.14, and here T is the temperature. So, here Pt, again Pt is equal to D minus 1 divided by D plus 2 into m by D, it is equal to Pi plus PO. So, here we can substitute the value of the Pi and here we can substitute the value of the PO, that is the orientation polarization. So, here Pt can be written as 4 by 3 pi n alpha plus 4 by 3 pi n mu square divided by thrice kT. So, let us consider this equation. So, here the right hand side, the first term, that is the induced polarization 4 by 3 pi n alpha. Alpha is the polarizability, it is a constant, n is constant, pi is constant, 4 by 3 is constant. So, this term is constant and it is denoted by symbol A. Then here in the second part, 4 by 3, it is a constant, pi is constant, n is constant, mu is the dipole moment, it is also constant, that is why mu square is also constant, 3 is constant, k is constant. Here T is the temperature, it is not constant. Here 4 by 3 pi n mu square divided by thrice k, it is denoted by symbol B. So, here B. So, this Pt can be written as, here it is a Pi, actually it is not Pi, it is a Pt. So, Pt is equal to A plus B by T, where A is constant and B is constant. The value of the A and B are given here, the temperature is not constant. So, Pt is equal to A plus B upon T, just it is as like as the y is equal to mx plus c. So, here let us plot the graph of Pt versus 1 upon T. Pt is the total polarization. So, let us consider the graph. So, here the total polarization versus 1 upon T for the polar as well as for the non-polar molecule. So, here carbon tetrachloride and the methane. These two are the non-polar molecule. So, the effect of temperature on the total polarization in case of the non-polar molecule, the value of the total polarization in case of the non-polar molecule, all the values are constant. That means, there is no effect of temperature on the total polarization in case of non-polar molecule. But here when we consider the polar molecule, that is the HCl and methyl chloride. So, here as we change the temperature, as we increase the temperature 1 upon T. So, here there is a change in the total polarization. So, these are the graph for the polar molecule as well as the non-polar molecule, that is the total polarization versus 1 upon T. Then here from the above equation we can say that the total molar polarization is linearly vary with the temperature, giving straight line when we plot the graph Pt versus 1 upon T. So, already we have discussed this. So, here when we determine the slope of the line, the slope is equal to 4 by 9 pi n mu square divided by thrice k. So, here by substituting the value of the n as well as the pi k, here mu can be calculated. So, here just substituting the value of the slope, here we can calculate the mu. So, here this equation can be reduced, mu is equal to 0.128 under root b into 10 raised to minus 18 ESU centimeter. By substituting the value of the pi n as well as the k, here this equation can be reduced to then this can be written as mu is equal to 0.128 under root b dBi, because all of you know that 1 dBi is equal to 10 raised to minus 18 ESU centimeter. So, here in this equation b is the slope of the line. So, in case of the polar molecule, so just substituting the value of the b in case of the polar molecule, we can determine the dipole moment for the polar molecule. In case of the non-polar molecule, this mu is equal to 0. So, here just substituting the value of the slope, we can determine the dipole moment of the polar molecule. So, here from the graph again we can say that as the total molar polarization or total polarization, it varies with the 1 upon T. We can say that they possess the permanent dipole moment, whereas in case of the this carbon tetrachloride and the methane, this Pt is independent of the temperature, therefore, they does not have permanent dipole moment, and all of you know that once again molecule possessing the permanent dipole moment are called as the polar molecule, and those without permanent dipole moment are called as the non-polar molecules. So, friends, in this lecture we have discussed the molar polarization in case of the polar molecule. So, what is the difference between the molar polarization in case of the non-polar molecule as well as in case of the polar molecule? In case of the non-polar molecule, there is only one polarization, and that is the induced polarization. In case of the polar molecule, there are two types of the polarization, induced polarization as well as the orientation polarization. That is why here Pm is equal to Pi is equal to Pi plus Po. So, here in case of polar molecule, there are two types of the polarization. Thank you.